Python 3.14 recently got released and it just got a major productivity upgrade. I'll show you exactly what changed, why it matters, and how to use it with side-by-side comparison with older version. This will be the most detailed video on Python 3.14. This version is packed with features that make coding faster, cleaner, and more intuitive. From smarter error messages to true concurrency. Let's begin. Welcome to DevNormal. My name is Vivek and I'm a software architect with 12 plus years of industry experience in building systems and applications in Python and other open source tech. I have delivered many talks and workshops in various tech conferences and events in India and abroad. So let's begin our journey of learning. In this video, I'll be talking about 8 new most important features that were introduced in Python 3.14, and we'll also see the differences with older version like 3.12. We will start with simple feature and then move towards the more complex ones. So let's begin with the installation. So to install the new version, I'll be using a utility tool called as PyEnv. PyEnv is a tool that can be used to manage and maintain all the Python versions that are there in the system. If I give the command pyenv versions, it will list all the Python versions that are available in my system. Now let's install the new version. The command would be pyenv install and the version number. And this will install the newer version. So installation has completed. To set the interpreter in PyCharm, I have to go to PyCharm settings and then select the interpreter from the list. So interpreter is now set. In order to confirm whether the right interpreter is set or not, just type the command Python in the terminal and it will show the version which is installed. As mentioned earlier, we will start with simpler features and then move towards more complex features. So the first feature that we are going to talk about is optional parenthesis while accepting multiple exceptions. Let's see the demo. I have written some code earlier that I'm pasting here to save some time. Let me explain the code, what's happening here. I have a very simple method called as division, which takes two arguments x and y. Both x and y are getting converted to integers. Now this might potentially give an exception if the value of x or y is not convertible to integer. For example, if I pass a string or any other object. On the other hand, if I pass the value of y as 0, then I will get 0 division error. So I'm trying to accept two exceptions here in a single line. And in order to do that in Python 3.12 in previous version, we have to use this parenthesis. Now let me run this code and see if it works. Okay, so it's working absolutely fine. Let me pass 0 here to accept 0 division error. And this is also working fine. If I remove this parenthesis from here in Python 3.12, then it will give me a syntax error. Now let me copy the same code in Python 3.14 and see how it works. So in Python 3.14, this parentheses here are optional. I can also remove it if I want to. Now if I remove it and if I run, it works. Whereas in 3.12, this gave me syntax error. Now one very important thing to note here is if I want to create an object of this exception, then I have to use parentheses. So suppose if I say for accept value error or 0 division error as ex and then print ex. Now in this case, I will have to put parentheses and it is not optional anymore. So this is the first feature, optional parentheses and try except when we are accepting multiple exception, only if we are not creating the object of that exception. Now let's move on to second feature. The second feature is also related to try except. In Python 3.14, if we add any control flow statement to finally block, then it gives a warning. Whereas in Python 3.12, we don't get any such warning. Let's see the example. So in Python 3.12, I'll be creating another program file, say demo2 try except. Now let me copy paste the same code that we have written earlier and add a finally block to it. So this is the code that we wrote earlier and let me add a finally block here, finally return. Now what will happen is, after it accepts, or if it doesn't accept anything, finally will always execute and it will just return from the function. So you see the output is none because it has returned from finally. And in Python 3.12 we don't get any warning. Whereas if we do the same thing in Python 3.14, then it raises a warning. Let's see. Now this is Python 3.14, and if I run this here, it throws a syntax error warning saying that there is a return in a finally block. For version 3.14, this is still a warning, but in future versions, it may actually become an error. Moving on to third feature, in Python 3.14, improved and better error messages were introduced. So the first example here is any typo in the keyword. For example, if I say for I in range 10, now here there is a typo in for, and if I run this, it clearly says, did you mean for? So it identifies which keyword we are trying to write, and if there is a typo, it identifies it. Now let's see the same example in Python 3.12, and if I run here, it just says invalid syntax. It doesn't give any other improved better error message, whereas in 3.14 we get a more improved error message. Another example of improved and better error messages is unterminated string, which is very common. So for example, let's say if I have a string that is not terminated properly. So if I'll run this, it says, is this intended to be part of the string? So it mentions like this word hello, which is outside both the quotes. Is it part of the string or not? So we get a more clear error message. Whereas if we put the same thing in Python 3.12, it will just give syntax error or invalid syntax. Let's look at another example. Example 3 is statement in expression context. What it means is, let's say if I have a variable is equal to 10 if true, else I can give here say 20. Now because the condition is true, the value of x will be 10. But instead of 20, let's say if I give here pass, this is unacceptable, and it mentions in the error message that it expects an expression after else, but a statement is given. Whereas if we do the same thing in Python 3.12, then it will just give the syntax error. Moving on to another example, misplaced elif after else. Let me copy paste the code. So it's a very simple code. X is equal to 5. If x is greater than 0, then print positive. Otherwise, print not positive. If it is equal to 0, then print 0. But this elif is coming after the else. Now let's see if I run it, what will happen. It clearly mentions that elif block follows an else block. Now this is not possible in Python. Elif block should come before the else block. So I have to put it here and then it should work fine. Now let's see if I put the same example in Python 3.12, then what will happen? And here it gives syntax error. The theme is very simple. In Python 3.12, it just mentions syntax error, whereas in 3.14, it gives more meaningful error message so that we can correct our code. So the last example with respect to this better or improved error messages is related to a mistake that many people make. For example, let me comment this existing code. So let's say if I have a set and then I'm trying to add some values to this set. Now what will happen if I try to add a list to this set? So this will give me an error saying that cannot use list as a set element. Whereas in the previous versions, if we see, it just says unhashable type list. Now same thing is applicable if we are using a dictionary. So for example, if I create a sample dictionary here and put a list as a key and some value doesn't matter. Now if I try to run this code again, it will give me the error saying that cannot use list as a dictionary key. Whereas same thing if I'll do in Python 3.12, it will just say unhashable type list. So this is all about improved and better error messages. I'm sure that this new improved and better error messages will help us in fixing our code quickly. So moving on to the next feature, in Python 3.14, it has introduced a new library called as Zstd. Zstd is a zipping mechanism that that helps in compressing the data or the file. It is developed by Meta and it is a lot faster than the existing mechanism in Python, gzip. So in this demo, let us see how Zstd works, and also we will compare it with gzip. So let's import the Zstd. We have a new library, inbuilt library called as compression. Let's import time so that we can measure the time in the time taken to compress the data. Let's add a function, say compress data. This method will take two arguments. One is the data that needs to be compressed and the compression module, whether it is gzip or Zstd. So let's pass compression module and the data that we have to compress. Whatever the module we are passing, whether it is gzip or Zstd, they both have compress method and we are compressing the data. So this method will return the length of the compressed data to see how much compression we have achieved, and it will also return how much time it has taken to compress the data. In order to measure the time consumed, we have to add some timestamps, time.time minus start. Now let me write the code that will execute this comparison. Now let's create some dummy data of big size that we will be compressing. In order to mimic the large data set, I'll just multiply this word with some 100 million maybe. These data compression algorithms, whether it is gzip or Zstd, they both take the data in the bytes form, not in the string form, whereas this is a string. So to convert it into bytes form, it's very simple. I'll just have it as a B string or a byte string. Now first let us try to compress the data using the gzip. The method will return the compressed data size and how much time it took to compress that data. Now let us print the compressed data size and the time taken. Also, to compare it with Zstd, let us call this method once again, but this time we will be passing the Zstd module. Now let me run and see how much time it takes. As we can see in the output, the gzip module actually took 14.28 seconds, whereas Zstd module for the same data, it took 0.61 seconds. We can easily calculate how much faster it is. In this case, Zstd is almost 23 times faster compared to gzip. Now, of course, it also depends on the data that we are having or the data that we are compressing. Here, the data is very simple. We were just having one Python word, which is repeated 100 million times. In real scenario, the word may not be repeated, so the compression will not be this much. But nevertheless, the Zstd is very much faster compared to gzip, no matter whatever the data we are having. Now let's talk about the fifth feature, which is called as t-string, and probably this is the most talked about feature which is added to 3.14. But before we talk about t-strings, let us get some basics clear, and let's talk about the f-string first, so that we will know what are the existing options we have and what are the new things that is being added by t-string. In these examples, I'll create some variables that I'll be using later on to create multiple f-strings or t-strings. Let's do a basic f string. Basic f string is very simple. We just have to put f before quotes, and inside this curly braces, whatever the variable we put, it will just replace the value. So if you print this, it will replace the name and the alias and give the string. Moving on to the next example, f string also supports expressions within the string itself. So let's say if I have this sentence, and here age minus 25 is an expression. It is inside f string, so it will first get resolved to a string and then it will be printed. If I'll print it, so it says 10 years, which is 35 minus 25. So we can also have expression in the f string. Another thing that we can do with f string is some formatting. Here we are doing some kind of formatting. So here, if we see at line number 5, net worth is 42 billion with lots of zeros. We cannot count the number of zeros here, but if I'll do some formatting and then print it, I can easily count it. So now you see it has added commas after every 3 zeros. The point here is f string returns you a string, and we can do expressions within the f string. We can also do some formatting within the f string. Now before we move on to t string, I also want to talk about something called as template, which is also available in Python 3.12. So from string, we can import the template and then we can create a template. The important point to note here is, in this case of template, we represent variable with dollar symbol, and even if we write expressions, this expression will never get evaluated. Now, second point to note here is, it returns a template object, whereas fstring always returns a string object. To get the resolved string object from this template object, we have to call the substitute method. So if you see, I'm calling the substitute method and I'm replacing the name, city and age, just like how we do in format as well. Now let me get these variables from the other program. So now if I try to print intro, and you see the expression is not resolved. So personally, I have never used from string import template. I have never used this kind of template to resolve the string. And I have not seen this kind of code in any of the popular library or in any of the code bases that I have seen in my career. Also, if we closely notice, this is very similar to dot format. Let me show how. I have copied the code here, and if we closely notice, in the intro template, instead of the template class, we are simply mentioning the string with curly braces, and instead of the substitute, we are calling the dot format. The same thing will happen. It will return me the string object and the expression will not get resolved. The only difference is in this case as well, in this later on case, the template is also of form string type, whereas in the template case, the template is of type template. So I see format is very similar to this template. So now that we have understood what is an f string, or what is dot format, or what is the template which is from string module, now let's look at t-string. T-string is only supported in Python 3.14. It is not there in previous versions. Let me copy the same example that I have used for the f string. So that it will be easier for us to compare. And I will do one more small change. Instead of directly printing it, let me put it in a variable. Let's name this one as intro template. So we have updated our example, f-string example with t-string, and I have named the sentences as template and then printing those. It is printing the template object. So t-string, unlike f-string returns you a string object, t-string returns you a template object. And this template object is different from the template that we saw earlier, which was coming from string.template. So let's not confuse this template with string template, both are different. So this new template object, this is coming from a new library in the string module called as template lib. So both of these templates are different things. From string import template, we saw it earlier here, where we were using the dollar symbol and this expression was not supported. And in the t-string, the new template that we are going to use is from string.templatelib. This is the new module. Now if I'll try to check the instance, okay, so this should be true. The t-string returns a template object which is coming from template lib. So in order to get the string out of this template object, we have to write our own template renderer. There is no inbuilt renderer for this. For example, in string temp or in the string.template, we were having the substitute method, and substitute method was returning the string object. In case of t-string, consider that you have to write your own substitute method, or you have to write your own renderer method. I can write different renderer for each template if I want to, but let me write a common one here, which will work for all three. But the idea is you can have renderer for different templates. Let's look at the t-string a little bit more closer. So if we see in the t-strings, we have two things. One is the strings and one is the interpolation. So first I'll just check whether the passed object is a template object or not. If not a template object, I am returning the type error. So after the initial check, I will iterate on every part of the template. Basically, we have two parts, the string part and the interpolation part. So we will iterate over these two parts and then we will create the final string out of it. And here, let's call it. And here we will pass the alias template. Now let me put a debugger here just to show you how this part looks, so that it will be easier for you to understand how this renderer will work. Let's look at this part object a little more closer. Here we have the expression name. This name is basically the variable name here, which we have put in the t-string. And the final value, if we see here, it is of type string and the value is Bruce Wayne. From where this value is coming? This value is coming from here at line number 3. So this interpolation object part, we are interested in just two things: expression and the final value. Let's clear it and I'll create an output list here. Here we see we have the strings and the interpolations. Interpolations we already saw, we can get the value using the value attribute, and the string objects, they are directly a string anyway. So what I can do is I'll just check here if the part is of instance type, is of string type. If it is a string type, I'll directly append it to the output. If it is an interpolation object, then I'll append the value of that part. At the end, I'll just join all these values together and return it as a string. So now my renderer is complete. Let's run and see if we can get the final string output from this. Let me print the alias. So as we can see, we are now getting the final string object from the template object using our renderer. Now let's render all the other template objects as well. So now I have called the renderer method on all the intro templates, net worth template and the alias template. Net worth template, okay, I have to make it t-string here. So we have an integer also here, and I just directly put the value here. Let's convert it to a string. So now we can see all the templates are being rendered properly. And here we can see that it also resolved the expression. So the final value that we are seeing here is 10 years. In this case, the expression is working fine. Whereas when we looked at the string template, the expression was not working. And in case of format also, the expression was not working. But in case of f string and in case of t string, the expression works properly. So now that we have understood what is the t string and how to render it, one can ask what is the advantage of it, or where can we use it, or how to use it in a proper way. The advantage is that, or the first advantage is that there is no immediate string resolution. Whereas in case of f string, the string gets resolved immediately. In case of string template or t string, it doesn't get resolved immediately. It will only get resolved once you write the renderer. And also the renderer you have to write on your own. There is no inbuilt renderer for the template. So you can render the string in the way you want it. Now what's the proper use of t-string? Like I said, it doesn't get rendered immediately. So this t-string can be used at places where we have to do some pre-processing of the input. For example, in case of HTML rendering, or if we are writing SQL queries, then we can remove the part where the SQL injection might happen. Let's see an example. I'll create a new file for this. So let's say this is my query template. Select staff from students where name is equal to some query input. And this query input can be a name of a person. What if I put a injection here? For a time being, let me convert it to f string and just show how this query will look like. So you can see the query is looking like select star from student where name is equal to Bruce, semicolon, and then we are dropping that table. So this is a dangerous SQL injection query. Now let me convert it back to t string and resolve this SQL injection. So I'm implementing the renderer method now for this SQL. So I'll create two lists here, let's say query parts and the actual parameters. Now let's iterate on each part of the template. And we will check if the part is a string type, then directly append it to the query parts. If it is not, basically if it's an interpolation, let's say here this query input will become an interpolation. So if it's an interpolation object, then what I am doing is first I'll break it at the semicolon. So it will get broken at here and here. And then I'll just pick the first parameter from that splitted list, or the first item from that splitted list. Let me typecast it to a string. The actual query will be formed by joining the query parts. Now let's return the parameters and the query. Now let's render our template. So as we can see, we are getting the parameters here as a list. And we are also getting the final sanitized query. And in the final sanitized query, we do not have the SQL injection part of it. So personally, my opinion is whatever I can do with the T string, I can also do with the F string. And now when it comes to the actual sanitization of the input parameters, whether in case of queries or templates or wherever, so instead of rendering the entire template, I can just sanitize the input value. Now let me try to do the same example with the F string. This will result in the final string with the injection part also. So what we can do now, I can directly sanitize this query input, and let me write the method for it. Instead of sanitizing the entire SQL, I'll just sanitize the query input. Now if I'll print it, you can see the final output is exactly same. Let me add the single quotes here as well. So we can see the final output is exactly same, whether I use a T string or a F string. As long as we know what we are doing, whether we have to sanitize the input or not, we should be good to go with F string as well. So I guess it's a personal preference whether you use F string or a newly introduced T string. T string gives you more customization, more flexibility, but the same thing you can also achieve it with the F string as long as you know what you are doing and as long as you are actually sanitizing the input that you're passing to F string. So with this, let's conclude the T-string topic and let's move on to the next feature in Python 3.14. We have covered 5 features so far and we were moving from the easier features to the more complex ones. This sixth one is called as deferred annotation. And before we move or before we talk about deferred annotation, let's talk about what is an annotation or how this annotation actually works. So let me create a demo example file for the annotations. So here we have a very simple method, add numbers, that takes 2 arguments. And we are saying that the first argument is of type integer. The second argument is also of type integer and the function also returns an integer. This is called as annotations. This is very simple. Now in Python, annotation does not actually force you to pass that object only. So here I can say add numbers and instead of integers, I can pass a string as well. So we can see there is no error. It means it is not forced whether you pass integer or not, but it is more like for the developers to know or for the user to know. It expects a certain type. But Python will not give any error if that error or if that type is not passed, but you might get an error later on. For example, let's say if I do multiplication here and then if I pass string, then of course the strings cannot be multiplied and I'll get error. It's more like a hint. It's also called type hinting. So it's more like a hint, like what type you need to pass. So this is annotation. So this is a very simple annotation. Annotations can get even more complex. But before that, let's see what is the advantage of it. So first advantage is helps catching the error early. Then it also improves the code readability. We know that what we need to pass. This type annotation also helps the some tools like MyPy to check this static type checking. MyPy is a very simple tool. It does the static type checking of the function or of the code. It makes code more reliable. And in bigger projects, it's easier to maintain the code when we put this type annotations. So the type annotation also works in case of earlier versions like Python 3.12 or even Python 3.8, 3.10. Let's put this in 3.2 and see it there. If I'll run, it will work. So let me pass here string and then I'll get the error. So this error is coming when we are actually executing the program. This is a small program, so we can easily see. But in case of bigger applications or bigger programs, we cannot easily see like if we are passing correct values or the type is correct or not. So in such cases, we can use MyPy to do the static type checking. So let's see how MyPy works. We will just install the MyPy using pip. So pip install MyPy. It will take a couple of seconds to get installed. And now I just have to say MyPy and the file name. So file name is demo9. So MyPy says that we have 2 errors. And of course we have 2 errors. It says that argument 1 is not compatible. It expects a string, but we are passing, it expects an integer, but we are passing string. Similarly for argument 2, it expects an integer and we are passing string. So MyPy helps in catching the errors early. Now let's move on to more complex annotations. So let me write a simple function, say foo. It just prints the text, nothing much. Because our intention here is to understand the annotations. Let's say I only want a string that is less than 10 characters. In order to achieve it, I'll be using a library called as typing. And here I'll make it an annotated object. So I'll say annotated type str, and the metadata will be say max length is equal to 10. Basically it is saying the length should not be more than 10. Now of course this is more than 10 characters. If I run it, I will not get any error, because like I said earlier, the type annotations are not forced. It is for hinting, it is for type hinting. And even if I'll use MyPy, the MyPy will not give any error, because MyPy ignores the metadata. This is more like a metadata to MyPy. And how it looks is, in Python even methods are object. They will have something called as underscore underscore annotations dictionary. So let's look at that dictionary for this foo method. If we see, this is what the annotations of the foo method looks like. Now this is the metadata, and MyPy cannot understand how to resolve this metadata, and that is why MyPy is not giving any error. But it knows that okay, it is a string. If I'll give something else instead of a string, let's say if I give an integer, then MyPy will give an error. So now the question is, how do we validate this advanced annotations even if MyPy cannot detect it? And the answer is there are two ways. One, we can write our own custom validators, or we can use some popular libraries like Pydantic. So here I'll be using Pydantic module. Let's install Pydantic. From Pydantic I'll import two things. And here instead of saying max length 10, I'll make it a field. And here I'll pass max length is equal to, if I run this, still it won't give any error because I have not validated it yet. So let me add the validate decorator. So after adding this validate call, now let me run it and see. Pydantic is actually throwing the error even before it is calling the method. So using Pydantic, we are able to know that okay, the string passed is not correct, or it is more than length 10. If I reduce it to, let's say, less than 10 characters, then it will work fine. So we can validate this advanced annotations using Pydantic or our own validator. Now let's do one more thing. I can actually create my own custom type using these annotations. Let me create my own custom types, say short str, and I'll put annotated str here. And here I'll just say short str. And let's say text2 will be a normal str. So in this case, it will work fine. But if I give more than 10 characters here, then it will fail, of course, because my first argument is not less than 10 characters. Okay, so now we know that using annotated, we can create advanced annotations. Using Pydantic, we can validate it, and we can create our own custom types. Let's create one more custom type, say positive int. It will be of type integer. It should be greater than 0. So now both arguments are correct. String is also short and the number is also positive. But if I give a negative number, then it will give me an error. So that's the power of annotation. We can tightly control our program and our code. So why we needed deferred annotation? Deferred annotation is also called as lazy annotation or delayed annotation. So why do we need that? And the answer is because this normal annotations in Python 3.12 has one very big disadvantage. It validates all the annotations eagerly as we load the program. Let's see what I mean. So in order to show the disadvantage, let me create another demo file and I'll copy paste some code here. We have already seen annotated. This integer is of type Fibonacci's 40th integer. And to calculate this, I have a recursive method here, and this is a time consuming method. So this looks very simple and it's not looking very harmful. But let me create one more file, and here I'll try to import this increment function. Increment function is very simple. It is just taking an integer and adding +1 to it. We import this increment method here. Now just importing this method, let's see how much time it takes. I'll just note the start time and then I'll measure the end time after the import. And then let's print how much time it actually took to import this module. So if I'll run this, so we can notice that it took almost 11 seconds to import this module. And why this 11 seconds? Because this increment method takes X argument, which is calculating this 40th Fibonacci number using this recursive call. So what I meant to show here is when we import a module, then it resolves all the type annotations while importing. In case of bigger programs, let's say if I have a a huge application where I'm importing a lot of modules, third-party modules, pip modules, my own modules, then imagine how much time it will take to load up everything. It will delay the startup. In case of bigger application, this becomes even more significant because we want to keep the boot up time low. But because of this eager annotation or eager annotation validation, the boot up time increases. That's the disadvantage. And to overcome this disadvantage, Python 3.14 has introduced deferred annotation or lazy annotation validation. Let's see how it works in Python 3.14. So I'll copy the same example in Python 3.14 and let me execute this import here. So you see here in Python 3.14, as soon as I ran this, it imported in 0.008 seconds, whereas in 3.12 it took almost 11 seconds. So that's the advantage. What it actually did is it simply imported it. It did not validate the annotation while importing. If it is not validating it, then how do we validate on demand? If I'll try to call the annotations of this increment method, while calling it, now it is actually doing the validation and it is taking the time. So now it has validated because of delayed annotation. It validated it when I explicitly called it. So once annotations are validated in 3.14, it gets cached. So every time it will not take this much time. For only the first validation it takes the time, but for the second and third validation, if we do, it will be using the cached value. Let's see. And before we move on, I wanted to point out one more important thing. This underscore annotation, it's a special attribute, and we should not be actually accessing this kind of special attribute directly. So in Python 3.14, they have introduced a new library called as annotation lib. From annotation lib, import get annotations. And here, instead of using this annotations directly, I will use get annotations. And I'll pass the object here, which is increment object. And let's see how much time it takes. So let me import the time module. Now let me run this and see. So this get annotations method, it also tries to access the same underscore annotations dictionary, and now it is doing the validation on demand, 15 seconds. In case of 3.14, it took even more time. So this much time we saved with the deferred annotation. Now let's see what will happen if we do it second time. So the first time when we ran it, it took almost 16 seconds. But when we tried to do the annotation second time, it just took 1 second or 1.4 seconds. It means that once the annotations are validated, it gets cached. And then if we try to access it again, it is actually fetching it from the cache. Now let's look at some more details of deferred annotation. I'll create one more demo file. Let me copy a very simple code here. So we are having an x is equal to 10 plus 20. And then we are having a user attribute, which is of type user class. This is not defined anywhere, hence we are getting this red line by my IDE. Let me copy the same code in 3.12, and if I'll run it here, this will give me an error saying that user class is not defined or user is not defined. But if I run this in 3.14, I don't get any error. It prints the value and I don't get any error. So it means this type of validation also is being deferred in 3.14. Now let's see how we can validate this annotation. So I'll import from annotation lib get annotations, and let me try to print the annotation of this user object. This is expected to give error, and I'll just explain you why. It says that user does not have any annotation. So why is that? Let's explore. Always make it a habit to look at the internal code of this kind of modules. This gives an idea how these modules are implemented or how to write the standard code. So let's look at here. And it says the object that we pass to it must be a callable object, a class object, a module object, or any other object with annotate or annotations attributes. Whereas this particular object, user object, it is neither a callable, it is neither a module nor a class, and also it does not have an or underscore annotation dictionary. We have a format, so we can actually print this annotation in 4 different formats. It's an enum. So we can print it in the value format, forward reference, string, or value with fake global. So if we look at the docstring in more detail, we see that if we pass the value format, it fetches the underscore annotations dictionary and returns it. Otherwise, if it is not present, then it will look for the annotate function and tries to call it. If we are calling with forward ref, then again it will first try to fetch the annotations dictionary, and then it will fall back to annotate. Whereas if we call for source, and I think this is wrong here, because source is not a valid format. The valid format is string. So maybe it requires a little correction here in this docstring, and maybe it's a good opportunity for one of you to make this small correction and make it your open source contribution. Replace this with string. So if you pass it as string here, it will first look for this annotate method. If it is not present, then it will fall back to annotations dictionary. Now moving back to the actual code, because this is not a module, not a class, that is why get annotation is not working here, and that is why it is giving an error. So let's load the module. And how to load this module? We will use sys module. First, we will load this module using the sys library, and here we need to give the name of the module, because I want to load this existing module, this existing code. So I'll just say __ name, and this module will be loaded. And now I can pass this module to get annotations method. Let me rename it to current module. Now I can pass it to get annotations, and then get annotations will validate this entire module, and then it will say, okay, this user type is not present. So now we are getting the expected error saying that user is not defined. Do you mean user? But if I do not do this validation, then there is no error. Now let's look at the class example. This is a module example. Let's say I have a class language, and I have the name here of string type. Let's call it programming language. Now as per definition, I can also pass the class to get annotations module, and I'll pass the class here. Class example, we can see we are getting this annotations dictionary back, and if we notice, this is exactly same as __ annotations. So instead of get annotation, I'll call here language dot __ annotations. The output is exactly same whether we call get annotation or __ annotation, because by default the format is value format. Now if I'll change the format, let's see what difference it make. Let me import the format enum from here. Format.string. So if we compare both the formats, value and string, in case of value, it is giving me the actual type of that particular object. Whereas in case of string, it is just putting that in the string format. That's all. So I have already shown this __ annotations in 3.12. But here in 3.14, this works in a little different way. Here it uses a something called as descriptor protocol, and because of descriptor, it is being delayed. Let me know in the comments if you want to know more about descriptor. I can make a dedicated video on descriptor. It's also a very interesting topic in Python. So in case of annotations, the focus is always on the type and not on the value. Even if I change it, let's say to integer, this will still work because the focus is on the type. So now the question would be why it did not give any error, because we are just getting the annotation. We are not validating it here, and annotation is always about type, whether it is defined or undefined. Here we have defined type, which is str. Suppose if I have an undefined type like user, then it gives an error if it is an undefined type. So it's always about type and not about the value. In order to validate whether the value is also right or not, then we have to do the validation like we have done earlier using Pydantic. So now let's change this example a little more. Earlier we saw an annotated type called a short str. Let me put it here, but it is not defined here. And because it is not defined, it is expected that this might give an error. But let's see how this different format work. So I'll remove this particular print statements. And first let's just print only the format.string. This will not give any error because it only prints the str type or the string value of that particular type. Now if I change it to value, then this will give me an error because value looks for the actual type, and the actual type of the short str is not defined in this module. So then this will give me an error saying that it is not defined. And if I give here another one, say forward ref, then also it will not give any error, because with forward ref we are telling to the program that this is not yet defined, but we will be defining it later on. And that is why here in case of forward ref, it says forward ref short str, it is of class type. So it will expect that, or it is expecting that it will be defined later on. Let me comment this value format because this will throw an error. I want to show one more thing. So let's say if I derive the language class and create another class, and here I'll use some other attribute, say version. So now if I try to annotate this Python class, then what will happen? Will it annotate only the attributes of this class, or will it annotate the attributes of its parent class as well? Well, as it turns out, it only looks for the annotation of its own class. When we are annotating a derived class, it does not look for the annotations of the parent class. So here we see, in case of Python class example, let me reprint it to show the difference. Okay. So in case of Python class example, it only shows the annotation of its own. It does not show the annotation of its parent class. So we have seen multiple types of deferred annotations, one in the methods, then while importing, then while in the module itself, in the class, in the derived class. Now there is one more type, which is circular import, and that is a very painful thing in bigger applications, because in most of the cases, somewhere or the other, we would get that circular reference error. So let's see how Python 3.14 handles the circular import. Let me create a new module, circular reference module A, and here I'll create a class. Let me also create the object of this class. Now let me create a similar thing for another module, say module B, and here I'll name it class B. Now what I'll do is I'll try to do circular import of both the classes into each other. And here I'll say related class. It will be of type class A, and similar thing I'll do in module A also. And here I'll say related of type class B. Now this is a circular import because in A I'm importing B, and in B I'm importing A. Now let's look at, or let's create a third module where I'll be using both class A and B. So let me import both the classes here, class A and class B. So now let me run this circular import thing in 3.12, and as we expected, it gives the error saying that most likely a circular import. And indeed it is a circular import, because in module A we are importing module B, and in module B we are importing module A. Now let's see how it works in 3.14. In 3.14 also I have done the import here, and then I am also doing the annotation on both the classes. But here it won't give any circular import error, and it directly gives the annotation of the classes that I have written at line number 7 and 8. So in 3.14, it does not look for circular import when trying to load the modules. So though there are many advantages of deferred annotation, there is one major disadvantage in my opinion, and which is partial execution. So if you look at this example here, it executed till line number 4 and then gave the error at line number 5. So it is up to you if you consider it as an advantage or disadvantage, but in my opinion, because it is doing a partial execution, so I think it's a disadvantage here. Now let's move on to the next new feature in Python 3.14, which is related to concurrency, and this is the most complex. With respect to concurrency in 3.14, we have two features. Let's see one by one. So the seventh feature in Python 3.14 is free threaded mode. Now what are this free threaded mode, or what are these free threads? It won't work on any build of Python 3.14. There is a very special build called as Python 3.14.0 T. T stands for threading or free threading. Even if you're using Windows, then for Windows also this T or special build is available. So let me install this special build, and then we can look at what is free threading. Pyenv install 3.14.0 T, and this will install the free threaded build of 3.14. So the free threaded build got installed. Now let me set this as the interpreter in 3.14. So here it is, and if you notice, this is the 3.14.0 T build, or the free threaded build that I'm setting as the interpreter. Now let me create the demo file to show the free threaded code, or the free threading feature. So I have created a very simple function here. What it will do is it will calculate the sum of the squares of all the numbers till range n. This is a CPU intensive task. Let me do it in a multi-threading environment. Let me import threading, and here let me also import time, so that I can measure how much time it took to actually run these threads. So here I'm creating like 4 threads, and to each thread I'll be calculating the sum of the squares till 10 to the power 7 till range 10 to the power 7. So before I execute this code in 3.14, I want to execute this in 3.12 just to show like how it runs in 3.12 without free threading enabled. So let me copy paste the code here. In order to execute, let me first call this method. So I'm calling this method here. Let me also print here if the GIL is disabled or not. I'll talk more about GIL. We can get whether GIL is enabled or disabled using the sysconfig. So if I print this, it says GIL disabled false. It means GIL is enabled, and it took almost 1.69 seconds in 3.12. Now let me do the same thing in 3.14. So here it says GIL disabled true. It means GIL is not enabled or GIL is disabled, and here it took only 0.63 seconds. Whereas here it took 1.69 seconds. So it's almost double or more than double in Python 3.12. So what's happening in 3.12? Why it took more time, or what is this free threaded environment in 3.14? Let's try to understand it with the help of a diagram. I have created or I have drawn one diagram earlier. Let me put it here. So in Python, we have something called as global interpreter lock, which actually puts a lock on all the resources, and any thread that want to use that resource, first it has to acquire the GIL lock, and then only it can use the resource. The resources can be the heap memory, the RAM. So what happens in 3.12? The GIL gives the lock to only one thread at a time. So it will not allow these two threads, let's say, and it will only allow this first thread to run. Then once the first thread is done the execution, then it will allow the second thread. It will give or it will lock out other two threads. And once the second one is done, then it will block, let's say, the first thread and the second thread and allow the third thread. So of course, it does not happen in sequence in real time. It can switch to any thread at any moment, and depending on which thread is available. So that is why in Python 3.12 or in previous version, even though we are doing multi-threading, only one thread is running at any given moment. And because only one thread is running at a moment, all the other threads are kind of running one after the other and not truly in parallel, even though they are using different CPU cores because of GIL. Now let's see what happens in case of 3.14. So in 3.14, it kind of allows all the thread to run at a time, and this GIL is more like disabled. So this GIL is not doing anything. GIL is disabled, and all the threads are running parallel all together, and that is why it is called free threaded. There is no GIL which is giving lock to anyone. All threads are free to run. The only disadvantage here is the code should be thread safe. Thread safe means if all the threads try to work on the same object, let's say if I have a list and all the threads try to append to the same list, then it's not a thread safe code, because all the lists will try to append to same list, and then that is not possible because you cannot have three objects at, let's say, one index. So that will give an error, and that's what the GIL prevents. But in case of thread free environment, the responsibility is on the developer to write code in such a way that it should not interfere with the threads. So that's how the free threaded environment works in 3.14, and this is the reason why we are seeing the less time in 3.14. Now let's move on to the eighth and final feature that I'll be talking about in 3.14, which is sub interpreters. That is also related to concurrency. And in Python 3.14, actually there is a lot of work which is done with respect to concurrency. We have now free threaded threading, then we have sub interpreters, then we have multi-threading, multi-processing, process pool executor, thread pool executor, interpreter pool executor, and then we also have async IO. So much options for doing the concurrency, and it really gets confusing. I'll try to simplify as much as possible. Still, if you have any questions, please let me know. If you want, I can also even make a different video or a separate video to show the comparison between all of these different types of concurrency or these different concurrency methods. For now, let's move on to the final feature, or the eighth feature, which is called the sub interpreters. So it basically runs the independent tasks in parallel, like how we have seen in case of free threaded multiple environment, but there the interpreter was only one and there were multiple threads. In case of sub interpreters, we have multiple interpreters. Why sub interpreters and why not multiprocessing? Because multiprocessing also has multiple interpreters. So the difference is, in multiprocessing, it spawns up new processes or new OS process or new OS thread. Whereas in this case, in sub interpreters, the process is only one, and because there is only single process, in single process we will have multiple interpreters, so the overhead of spawning multiple process is gone. So that is why these sub interpreters are little more faster, because there is no overhead of spawning the new process. One more point is, it is only limited to C Python. Iron Python or PyPy or other implementations of Python do not have the sub interpreters feature. Now let's move on to code. So let me create another file here, say generate data files. So a very simple code. What it will do is, it will just create two files, file1.txt and file2.txt. It will iterate for 1 million time, and it will append the random word out of this word list 1 million time. Let's create these two files. So we have now got these two files, and as we can see, we have all these words here randomly inserted in these two files. I'll be creating another helper file here. So as you can see, it's very simple. We are giving the file name and the word. It will read that file, and then it will split the text into words, and then using the collections counter, basically it will count the frequency of every word, and then it will return the frequency of the given word. Here I have also added a delay of 2 seconds, so that this will take at least 2 seconds to calculate this counter. Now let's move on to the sub interpreter code. First thing is, let me import that count word method from the helper module. Let me also import time to measure the time it takes. This is the new module that got introduced in Python 3.14. We will import from concurrent import interpreters. This is the new module. Let's mark the start time, and I'll create two interpreters here. Now let's say for the first interpreter, or I want to calculate how many times apple is repeated in that file. In the second interpreter, I want to calculate how many times orange is present in that file. And then I'll call this interpreter module. So I'm calling the .call method here, and I'm passing the word, this method count words, which will actually do the counting. And I'm passing the file name and the word that I want to find out. These two are basically the arguments to this method. So this method takes two arguments, file name and word. And that's what these two arguments I am passing here to this call. So the method and the arguments to this method. Now let me do the same thing for the second interpreter. Let's say orange count, and here I'll count it in file2 orange. Now let's see how much time it takes to calculate this count. Let's run this. If we notice the output here, we can see that the execution took almost 4.26 seconds, and each method or each process will at least sleep for 2 seconds. So this indicates that both the interpreters are actually executed one after the other, or the serial execution has happened here. Why is that happened? Is there only one GIL for concurrent interpreter? So the answer is no. For every interpreter, it has its own GIL. So it should be parallel. It should not be in serial order. It happened in serial order because I called it in serial order. Now let's see how we can actually run it in parallel and take the benefit of multiple or sub interpreters in parallel. So let me create another demo file where I'll run this in parallel. Let me make the same imports that we have seen earlier. And here, instead of interpreters, I will import something called as from concurrent.futures import interpreter pool executor. I'll create the interpreter pool object, and here I can give max workers also. Just want two interpreters basically as executor. Now I can submit to this executor, and what I can submit to it, I can submit the method that I want to call and the argument to those methods. Now let me call another submit for file2. This executor.submit will return a future object or a promise object, you can say, and then we can call on the result on that promise object to get the final output. Futures, and I'll create a list of these two executor.submit object. Now let's collect the result of these two submitted tasks. So I'll say results is equal to, I have to call the result call on the future object. So first let me iterate on the future object, futures, and here I have to call dot result. That's all. And then let's calculate how much time it took to do this entire thing. Now let me print the results, and if I'll execute it now, we will see it just took 2 seconds. We got the count of apple and orange from two different interpreters, and the final result is 2.18 seconds. So this shows that both interpreters actually ran in parallel. Now, one more advantage here is this concurrent module actually made multiprocessing, multithreading, all of this very simple. Let me change the interpreter back to the normal 3.14 instead of free threaded 3.14. Now, let's see an example of multithreading with the help of this concurrent module. So let me create another demo file. Now, earlier we saw that in case of multithreading, we had to do so much of work. We had to create our own threads. Then we had to do the start, join. We have to import that this threading library and all. But now with the help of concurrent module, it is even very simple. Let me copy the exact same code that we wrote for sub interpreters. And here, instead of interpreter pool executor, I will call thread pool executor. Everything else remains same. It has same interface. It means dot submit will work, dot result will also work, and it will be a multi-threading. It will be a multi-threaded code. Now let me execute this and it works. Now let's look at multiprocessing. So let me create a demo file for multiprocessing. Let's copy the same code again. Now instead of thread pool executor, I will call process pool executor, and here I'll call the process pool executor. That's all. So this is the reason I really liked this concurrent feature or this concurrent module. It has made multi-threading or multiprocessing extremely simple. All we have to do is call that executor or that pool executor and just submit the method to it. We don't have to do those join and start and all that. It all is taken care. Or we can convert a multiprocessing into sub interpreters by just changing the pool executor, or we can convert a multi-threading into multiprocessing or multiprocessing into multi-threading, or any way we want. So now let me execute this process pool executor, and if I'll execute this, I'm expecting an error, and I'll tell you why. So it says a process was terminated abruptly, and why it is abruptly terminated? Because in case of process, like I said earlier, when we do multiprocessing, it spawns new processes, new OS processes, and what's happening is, because this process pool executor, it is basically a wrapper over multiprocessing, it will create new processes, and every new process will try to execute this entire module from top to bottom. So this first process will call the new process, and the new process will again call this entire thing, and again call process executor, and then again this recursion will continue. And because this will become an infinite recursion, we are getting that error. So in order to avoid it, what I will do is I'll simply put this inside this condition, if underscore name is equal to underscore main. And now if I'll execute it, I'll get the output. So again, it's 2.17 seconds. So we see that with this concurrent, implementing multiple interpreters, multi-threading, multiprocessing, it's all extremely simple now. Now let's look at the differences visually with the help of a diagram. So I have created this diagram earlier, and let me show it. So in case of sub interpreters, you see we have only single process, whereas in case of multiple processing, we have multiple processes, and each interpreter has its own GIL. Here also each process has its own GIL. And in case of multi-threading, we have single process, single interpreter, single GIL, which is responsible for all of these threads. Whereas in case of sub interpreters, it is again single process, but we have different interpreters. So I hope this diagram makes it more clear how these things are working. All of these are giving us parallel processing, but in a different way. For example, multiprocessing has an overload of creating the multiple processes. Multi-threading has the overload of maintaining the GIL, and sub interpreter has the single process. That's all about concurrency. We have seen many different ways of achieving the concurrency in Python 3.14. We haven't discussed async IO at all. So let me know if you want to see a more comparative video of these different concurrency models. So that's everything new and exciting about Python 3.14. From smarter error messages to deferred annotations to different types of concurrency models, we have seen it all. If you found this breakdown very helpful, then please like, share, and comment. Let me know any questions you have. Let me know any suggestions that you would want to see in the future videos. And also let me know which feature you are most excited to try out. Thank you.